And we also know from the current equation, VGS minus the threshold voltage quantity squared will equal to ID over 1/2 mu n COX times W over L from the current equation. Now we can solve for VGS, so we can say that or VGS will equal to the square root of ID over 1/2 mu n COX W over L, and then add the threshold voltage to it. Now this is the trick. Since Vn2 minus Vn1, the differential input voltage, is the same as VGS2 minus VGS1, then we can say that Vn2 minus Vn1 will equal to, now we're going to substitute for VGS2 in terms of the square root equation. This will equal to the square root of ID2 over 1/2 mu n COX W over L minus the square root of ID1 over 1/2 mu n COX W over L. And the threshold voltage is cancelled out because I have the threshold voltage of VGS1 cancels the threshold voltage of VGS2. Now I can take the partial derivative of delta ID with respect to delta Vn, which is nothing but the partial derivative of ID1 minus ID2 over the partial of Vn1 minus Vn2. Now you take the partial derivative explicitly and then you do some algebra. So after some algebra we get alpha delta ID over alpha delta Vn will equal to 1/2 mu n COX W over L times 4 times ISS over mu n COX W over L minus 2 times delta Vn over the square root of 4 ISS over mu n COX W over L minus delta Vn squared. Now remember that this is the large signal, right? Now what we're going to do is we're going to have this explicit condition. We will say that we are interested in the large signal analysis, but we're going to start with the DC component. So we're going to say that delta Vn DC equals 0. What you do here is we're saying that the large signal analysis force the delta Vn to be 0, then the differential gain will equal to alpha delta ID over alpha delta Vn at delta Vn equals 0 at this DC biasing condition times Rd. And that basically will equal to the square root of mu n COX W over L times ISS times Rd. Whereas ISS here is the biasing current, which is ID1 plus ID2. Then the gain may be expressed as Gm, which is here, Gm is the transconductance of the amplifier times the output resistance Rd. And that is basically the square root of mu n COX W over L times ISS times Rd, where the transconductance of the amplifier, which is Gm, is equal to the square root of mu n COX W over L times ISS. Here is the summary of the large signal derivation. Here is the first point. If the two half circuits are identical and the DC gate voltages are identical, that means the DC Vn1 equals to the DC Vn2, then the differential DC output voltage is 0. Make sure that this is the DC differential output voltage. If the input differential voltage is not 0, then the differential input voltage is amplified at the output. So let's show you a graphical representation of what's going on here. Let's the horizontal axis to be the delta Vn axis, and the vertical axis, which is the delta ID axis, is basically ID1 minus ID2. what we realized is if delta Vn is more negative, then ID2 will be bigger than ID1. And by making delta Vn negative, we start to realize that the current ID2 minus ID1 start to reach saturation toward ISS, which means that all of the current that flowing from the biasing current source will be supplying the transistor M2. And if delta Vn is more negative, we start to realize that most of the current will go through ID1, and the current through M1 will increase by increasing delta Vn until we eventually reach ISS.